This is the multi-layer perceptron. We have two input, one hidden layer, one output layer, and two output. And in this video, we are going to show how can we apply the backpropagation algorithm to update the weight. So let's start from the output weight, W211 as example. Why do we start from the output layer weight? Because this one is directly related to the desired response, which is easy to update or adjust. And after this, we can discuss how can we update the weight in the hidden layer. So here we use the W211 as example. That is the weight for the in the output layer. So here we can see if we want to update the output layer W211, all this component will be involved in the update. Those are the input Y11 and the output of V21 and the activation function in the output layer is the V21. Of course, this is the output of the output layer Y21. And then will be the desired response D1. So all these components will be involved in the update of the W211. That is the weight for the output layer. So here we want to truncate this part because all this will be related to the update for W211. So here will be the figure about the W211. This is the weight we are going to update. Okay, look at here. For the V21, that is the output of the neuron of the of this one. So the V21 equal to the Y11 multiplied with W211 and then plus the Y12 multiplied with W221. So you can write as a general equation like this. The V21 equal to summation J equal to 1 to 2, and the WJ1, J means, you can see, the J means from J's input, 1 means 2 for this neuron, and 2 means that is the second layer, the output layer, and then multiply with the Y1J, could be Y11 and Y12. So this is the output of this neuron, the processing unit. And then the V21 will be as the input to the activation function phi21. Therefore, we can get the output of this one, of the activation function. That is the Y21 equal to phi21 as with the input of V21. So now we get the Y21. And from there, we can calculate the error, the E1. E1 equal to D1 and minus Y21. Okay, let's go through the whole structure one more time. So here we want to update the W211. This is the weight we are going to update. In order to update this weight, all these components will be used in the update. Start from Y11, the V21, V21, Y21, E21, E1, and D1. All this is going to use in the update of the W21. So here you can see the input Y12 will not going to be used because this one not directly related to the W21. So here we can see for each steps we can get the V21, we can get the Y21, and we can get the E1. So this is all the components we are going to use to update the W21. So how can we update the weight, the W211? This is just use the approach we used in the previous chapter. So the W211 n plus 1 means the updated one. equal to the W211N. N is the current weight, and plus the delta Wn. The delta Wn is an adjustment, just how much we need to add into this current weight. So the goal here is to find the optimal weight W211. So what is the optimal weight? That means the cost function, we do the derivative of cost function respect to the W211, that equal to 0. So here we use the star, the superscript star to indicate that is the optimal weight. This is exactly as what we did in the previous chapter. We find the optimal weight. Remember, in last chapter, we know if we can define the cost function, and this is their cost function. And this will be the optimal weight, the W star. This is the epsilon. Epsilon is the cost function. So what is the optimal weight? Optimal weight means the cost function do the derivative with respect to W, that's equal to the minimum value. Slope equal to 0. That is the optimal value, the optimal weight. So here is how can we apply the method for steepest descent approach to find the optimal weight for the hidden layer. So here is how can we update the synaptic weight? The W211 n plus 1 is the updated weight equal to the current weight plus adjust factor, the delta Wn. So the delta Wn equal to this one minus eta multiplied with the cost function derivative respect to W21. This one is nothing, but is the steepest descent method. So in previous chapter, in our MATLAB experiment, we show how can we write the code for this the steepest descent method. So the eta is the step size or adjust factor. Step size or the adjust factor. So we know for the steepest descent method, they have their advantage and has their limitation. The advantage is it's pretty straightforward. It's very, very simple. The limitation is the truth of eta could be really tricky. If the eta truth is too small, it takes really long time to converge to the optimum point, optimum weight. If the eta truth is too large, your adjustment will be jump back and forth, never can really converge to some point. Right? This is the advantage and the limitation of a steepest descent method. And in your project, you use the Newton-Gaussian method. That is really more advanced compared to this steepest descent method, but it needs a lot of calculations. So here in this example, in this chapter, we will apply this simplest one, the steepest descent method. So delta Wn equal to minus eta multiply with the cost function derivative with respect to the W211. The cost function equal to this, equal to 1 over 2 multiply with the E1 square n. So this one means square, not this is a square. So it's not a superscript to indicate which layer, but this is just the square. So look at it here. This will be the E1. You need to find the cost function epsilon equal to 1 over 2 and the E1n and then square. This is the cost function. Okay, so we are going to use this one to update the weight in the synaptic weight, synaptic weight in the output layer.